begin. Okay, let's go through a quick recap of what we learned last week, guys. A quick one here. If you look here, these are essentially a transverse wave, right? I mentioned that in a transverse wave, there are a few things you need to know, mainly the crest. COVID? COVID. Or is it? Anyways, the crest, the trough, which are either the top or the bottom of the wave. This is basically going to be the amplitude that is responsible for the... What's it responsible for again? Amplitude, what is it associated to again? Good, it is the loudness of the sound. Very good, Abigail. Right, so the loudness of the sound, the greater the amplitude, the greater the loudness, and of course, this is the wavelength. Like I mentioned, you could start from the equilibrium position, or you could start from the crest, or you could start and end at the trough. All these are considered one wavelength. All right. Then after that, we also talked about frequency. Frequency is directly responsible to the pitch of the sound. Guys, always remember that the higher the frequency, the higher the pitch, right? That's why men and women have different soundings, right? It's simply because our voice box vibrate at a different pitch. The frequency is basically, if let's say, for example, today I see 100 hertz, it means to say in 1 second, I can complete 100 oscillations, whereas if I have 200 hertz, in 1 second, I can complete 200 oscillations, right? Very important. That's why the definition is the number of complete waves produced per second here. Okay, very important. And after that, this formula, very important as well. Later, when we do the exercises, we are definitely going to be using these formulas here. V equals to F lambda, guys. Velocity of the wave depends on the frequency and also the wavelength of the wave here, right? Then after that, we also talked about a longitudinal wave. A longitudinal wave basically comprised of compressions and also rarefactions. In your IGCSEs, if they ever ask you to define compression, you have to state that compression is a region of high pressure. That's why the molecules are much closer together. Whereas for rarefaction, obviously it is a region of lower pressure, and thus the molecules are further apart, as you can see here, right? If they ever ask you for examples of longitudinal waves, it will always be either sound or ultrasound. Very, very commonly asked in your paper too. You must know this. Every other wave is going to be a transverse wave, except for sound and ultrasound, right? And then if we're talking about sound, the audible frequency is anywhere from 20 to 20,000 hertz. But as we grow older, our audible frequency is actually going to shrink smaller and smaller and smaller. And thus, when you're old, you'll always not hear what your grandkids are saying to you, right? I also want to highlight one more thing now, guys. In terms of the definition of a longitudinal wave, we define it in terms of vibration and also propagation. The vibration for a longitudinal wave is parallel to its propagation, whereas a transverse wave will have vibration perpendicular to its propagation. For those who are unsure of this or forgot about it, please revisit the video that I sent into the group chat. I think it's definitely going to be helpful, especially if you're going before your exams, right? These are the things you need to know, guys, very important. Then, yeah, these are examples of transverse wave. Any other wave is going to be a transverse wave. Light lah, water lah, electromagnetic wave lah, any wave under the sky is going to be a transverse wave, except for sound and ultrasound, which are longitudinal waves. Okay. And last week, I also introduced you guys this word known as wave fronts, right? Wave fronts are basically these things here. Wave fronts is a top view of the side of the wave. Imagine it from the side view, the tank looks like this, right? They have the wave, they are squiggling up and down, right? When we look from the top angle, we'll only see the crest of each of it, which is the wave fronts here, guys. These things here are these wave fronts here, okay? Very important. And after that, I also mentioned that in terms of water wave, it will go through three phenomena, so all right. It's known as reflection, refraction, or diffraction. Reflection is very straightforward. It's like what you see in the mirror every day. That is essentially reflection. Refraction is the reason why your straw bends when it's inside the water, guys. If you've ever seen your straw, oh my God. If you've ever seen a straw in the glass cup, right? You'll see that it kind of bends a little bit. This is due to the change in speed of light. Always remember, refraction occurs because there is a change in speed of light. Very, very important. You'll learn this later on in light waves as well. But for water waves, it's the same concept. Refraction occurs because there is a change in speed of light. Okay, whereas diffraction is just the spreading of the wave. We went through a little bit things here, guys. In terms of reflection, refraction, and diffraction, I said one thing was very important. What doesn't change again? Good, excellent. Frequency will never ever change regardless of the phenomena. All right. Frequency will never ever change, and because of that, in your IGCSEs, if they say what happens to the wave after reflection, refraction, or diffraction, the answer is always standardized. It is always never ever changes. Very important. You need to know this. And in terms of reflection of wave, I also introduced that the incident angle and the reflected angle is always with reference to this normal line here, guys. For those who cannot remember, a normal is an imaginary reference line that we use to measure the angles. It is usually 90 degrees to the surface where the light hits. So imagine the light hits here, then the normal will be here, but it will always be 90 degrees. Very important, the normal here, like a lot of students always get confused with this. You just have to know that it's an imaginary line that is perpendicular to the surface wherever the light or water hits. Okay, so same thing like if it reflects here, then this will be a reflected angle. Very important. Yeah, you guys should know this. For those who do not know, please make sure you go back and watch the video, especially for those who didn't watch it. All right. So yeah, then after that, refraction of wave. Guys, as last week I told you a story about how to remember whether it will travel fast or slow, right? Do you guys remember the story or not? What story reference were we using? We were at a where? Good. We were at a beach. Very good, Abigail. You still remember this? What did I say about the beach? The beach, if you're at a surfing beach from super far away, the waves are damn what? Damn taller, right? And then as it comes closer and closer and closer, the waves become smaller and smaller and smaller. This was because of good. In the deeper region, the speed is good. In the shallow region, the speed is slower. And because of this, once we associate that a deep region, the speed is fast, the shallow region, the speed is slow, we can combat all these refractive waves already, right? Refraction. If I look at the first example here, I mentioned last week that in a deep region, right, if let's say the barrier is straight line like this, if the barrier is straight line like this, the side view will look something like this, right? This will be the deep region and this will be the shallow region. If the barrier is straight line like this, as the waves enter the deep to shallow region, what's going to happen is you straight away see that the wavelengths actually decrease. This is because it is with accordance to the V equals to F lambda formula, right? If frequency is the same, a decrease in speed is going to decrease the wavelength. But I also mentioned that they'll never ask you this question in your IGCSE because it's too damn easy already. Instead, they love to give you these kind of questions here, right? In your IGCSEs, what will they give you? They'll give you this line, 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 and this line here. Everything from the shallow region is not given. So if you are asked in your IGCSEs, guys, remember how we do it? Let's say if we ask you something like this, right? And then after that, the waves are coming like this, and like this. Okay, this is the deep region, this is the shallow region. First things first, we always draw the original wave. If there was no shallow and deep region, the wave was supposed to be one straight line like this, right? Right. Then from here, we remember that, oh, deep going into shallow, the velocity here is fast, the velocity here is slow. And because of that, from here, I know that it's slowing down, right? And the word that I used last week was the wave is lagging behind. Excellent job, everyone. Right, it is lagging behind, and because it is lagging behind, will it tilt right or will it tilt left? Left, very good. It is lagging behind, right? So with this reference point, I can start drawing all the others, making sure that they are all parallel to each other. But of course, you don't draw the arrow, right? Because this is not mathematics, right? But from the eye level, it must be parallel to each other. Very, very, very. Okay, and if it's shallow to deep, if it's shallow to deep, then obviously it will be the other way around, or it will be like this and like this. Right. I'm sure everyone has drawn this by now. It's just a quick recap. Yeah, and then these things you need to know as well. Okay, let's go into diffraction today. Last week, I think I asked you guys to draw it, right? I haven't explained to you guys diffraction before. Okay, now diffraction, guys, if you want to understand diffraction is essentially the spreading. It is the spreading of the wave. Meaning to say, right, if let's say I have waves, if I have waves coming in from here, right, as soon as it passes this barrier here, what's going to happen is it is going to spread either a lot or it's going to spread very little here. Okay, now the spreading of the wave depends on one specific thing only. Everyone pay attention now. The spreading of the wave depends on whether the wavelength is larger than the gap or is the gap larger than the wavelength here. What do I mean by that? Now, in your exam, right, they'll probably give you something like this, okay? Yet again, they'll draw you this box here, right? And then they'll draw different scenarios, okay? They'll say that, okay, right now this gap is like this, and this gap is like this here. Okay, then they say that the wavelengths are coming in like this. Okay, they say that the wavelengths are coming in like this. Now, like I mentioned just now, the spreading of the wave depends on whether the wavelength is larger than the gap or the gap is larger than the wavelength. In this scenario here, clearly we can see that the wavelength is definitely much larger than the gap, right? If the wavelength is much larger than the gap, right, what's going to happen is diffraction is actually going to occur more. If diffraction occurs more, it means to say the waves that are after this gap will not retain its straight line, and it will look more like a Wi-Fi signal. Okay, remember our Wi-Fi signal, and there is a key component to drawing these Wi-Fi signals. Some students like to draw it like this, and some students they like to draw it like this here. They like to draw it like this here, right? Now, first and foremost, when we draw the diffraction of the wave, you must understand that diffraction occurs from the opening of the gap, right? So when you draw the first Wi-Fi signal, it should be at the opening of the mouth, not like this, and definitely not here, right? It should be at the opening of the mouth here. Okay, when you have identified that it's going to go through a lot of diffraction, it's more circular, right? Circular. But the key thing here is that when diffraction occurs, the speed, the frequency, and naturally the wavelength does not change as well. And because of that, if let's say here to here, right, it looks like it's 5 cm apart, right? When you draw the diffracted waves, they must look like they are 5 cm apart. I mean, you don't have to be exactly right, but from the eye level, it must seem like they look like the same wavelength, guys. This is actually one of the criteria in the mark scheme as well. Meaning to say, if you do something like this, you'll lose your mark. If you do something like this, you will definitely lose your mark. You want to try to draw the wavelength to be the same after the diffraction. So how does the direction of the wave go? Initially, it's going to go like this, right? Initially, the wave is going to go like this, but after diffraction, the wave will be spreading. It will be going in all different directions here, simply because the wavelength is larger than the gap. Very, very important. Before I proceed on, anyone don't know what I'm talking about for this part here? Good, excellent. If everyone can understand what I'm talking about, then let's see what happens if the wavelength is smaller than the gap, guys. Today, of course, besides this, there will be a second scenario, which is going to be something like this. Okay, right now, the gap is obviously much larger than the wavelength. But I don't want to be that big. Wavelength, yeah. Wavelength is that. Okay. Okay. So from here, we can clearly see that yet again, the wavelength this time is much smaller than the gap. And when the wavelength is smaller than the gap, the diffraction is actually going to occur less. If diffraction occurs less, what's going to happen is it will not spread out so nicely. It will still spread out a little bit, but in a much more squarish manner, like for understanding sake. So if it's much more squarish manner, it will still kind of look like the Wi-Fi. It will kind of look like the Wi-Fi, right? But this time it's much more squarish in terms of manner, in a way that they actually retain most of its straight lines, right, guys? You can see like here, straight line, straight line, straight line, straight line, straight line, right? Here also straight line, and also straight line. Some of the waves will be diffracted, which is this part here, 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 and also this part here. Okay, it doesn't get the Wi-Fi signal, it will get a more squarish Wi-Fi signal. So if I were to draw the direction of the wave, how will they move? Initially, it's moving like this, right? Moving like this, moving like this, moving like this. Now, some of it will still move straight, but some of it will be spreaded to the different regions. And this occurs when the wavelength is small. So one way you could associate is that when wavelength is large, diffraction occurs more. When wavelength is small, diffraction occurs less. Wavelength and diffraction, they are kind of directly proportional to each other. X means to say the gap here. This is the gap. The gap in the barrier. Okay. Everyone don't know what I'm talking about? 100% absorption rate, just what I like. I'll send this to the group chat for reference later on. I think the drawing here is not so nice, but this was the only thing I could find from the internet. So you'll see that actually this gap here is much smaller than this wavelength. So it's actually not supposed to spread so much, but if those who have drawn it already, it's okay. For those who need a reference, this is a more accurate drawing of how your IGCSE is supposed to look like now, right? The larger gap, then the larger the diffraction, the smaller the gap, the smaller the wavelength, the smaller the diffraction. Large wavelength, large diffraction, small wavelength, small diffraction. Very easy to remember. Okay. Yeah, then of course, the diffraction does not only occur in the gaps, guys, depending on how sound is traveling, guys. If let's say this is a sound wave, right? Depending on the wavelength, it may diffract more or it may diffract less. For example, if today, actually, let me try to find you a nice picture. Wait. Okay, guys, look at this example here, guys. Today, if this guy here is playing an instrument of low frequency, so it has low frequency, so it has high wavelength, versus high frequency, so it has low wavelength here, right? You'll see that diffraction occurs in the corners of the walls as well. You can see that obviously the one that has larger wavelength diffracts to everywhere, meaning to say this guy here can hear it, but that which has more smaller wavelength, it actually doesn't go through much diffraction and it will retain most of its straight line, guys. This is one of a concept example that will also be asked in your IGCSEs, guys, meaning to say diffraction is not only limited to water waves, it could be for sound waves as well. And yet again, the larger the wavelength, the more diffraction is going to occur. Okay, everyone? Yeah. Good. Everyone understand? Then this is the example that I was trying to show you guys. You can see here that, I mean, this diagram looks a bit sketched out or stretched out, right? But in reality, this one actually has more wavelength, right? And because of that, it will spread down more. This one has a less wavelength, and thus it doesn't spread down as much, guys. This is what you're supposed to understand from this diagram here, but I kind of stretched it out a little bit, so it looks somewhat similar. But they are definitely not the same, guys. One has larger wavelength, diffracts more, one has smaller wavelength and diffracts less. Okay, everybody. Who's missing from class today? Jihin is here, Jaden is here, Raj is here. And who's missing? There's one more guy that was supposed to be online. Who is missing here? Oh, Leha. Leha is missing. Where is Leha? Okay, but yeah, same concept also lah. Some things remain unchanged and some things may change. Write this down for those who didn't write this down. Frequency will not change, speed and wavelength will not change. These are all the V equals to F lambda. But yet again, the direction and velocity changes because velocity is a vector quantity. When the direction changes, velocity is bound to follow, guys. All right. Okay. Now that we're done with this, I'm going to copy later on when you're back at home for the drawings. Make sure to draw it down for reference. Okay, once we're done with this, we can go do some simple questions today together. I'm going to give you guys 5 minutes. Not 5 minutes. You probably need less than 3 minutes to attempt this question, guys. 3 minutes, guys. Let's attempt this right now. We'll discuss the answers exactly in 3 minutes, which is 11:30. Do this right now. Oh, yes. On figure 8.1, don't draw at the bottom. On figure 8.1, draw this way. No. But you also doing the same thing. No, it's not going to be there. It's supposed to be on the current existing wave. What happens if I have a louder sound? What are you supposed to draw? How, when you see the word louder, what's the first thing that comes into your mind? What do I have to change? Oh, good, very good. It's the amplitude, right? If I want to change the amplitude of this wave, how will it look like? This current wave that you have, not the continuation, this current wave that you have, if I have a louder amplitude, how will it look like?
Oh, so we go here.
Yes. What? Oh, yeah, that's correct. And that looks a bit weird. How come it's so sharp like that at the top? I think what she did was correct. Yes, very good. Excellent job. That is exactly what I want. Okay, everyone. I think everyone attempted this question already. Let's go through the answers real quick. Anyone that get any one of this wrong, I'm gonna physically abuse you for those who are here. Look at the first question. Which distance represents the amplitude of the wave? Circle your answer. What's your answer, Rachel? Good, excellent job. It is definitely going to be DE, right? Because it is always from the equilibrium to the depth of the trowel or the height of the crest, right? So it could be either here or it could be either here, right? Straightforward. Which distance represents the wavelength, Abigail? Sorry? AC. What's wrong with AC? How do we define a wavelength again, Abigail? It is the from where to when? Or it is either from the crest to the crest, or the trowel to the trowel, or the equilibrium to the equilibrium, right? If you say AC here, do you think this is one wave? Then this is second wave, this is third wave, this is fourth wave, this is fifth wave, this is 6, 7, 8, and 9. Is this the wave? It's supposed to be where? Nani, A to B. You think this is one wave? This is one wave. Where? E, A to E. Are you trying to like scramble random answers? There's not even an option to go from A to E, dude. Look at answers correctly. Oh, and the options available again. What is available? How did I define the wavelength again? It is as soon as it repeats itself, right on, Abigail. Right. A to B is repeat itself, man. A to C is repeat itself, man. A to E definitely doesn't look like it's repeating itself. Where to where it starts repeating itself already. There's only like 5 options. Good. C to F is the more logical answer, right? Right, C to F, because here it go down, down, up, down, repeat, down, down, up, down, repeat, down, down, repeat. You know what I'm talking about, right? Right. So always remember, wavelength is as soon as it repeats itself. And then when you draw the amplitude, guys, I want to highlight one thing when you're drawing the amplitude with the louder sound, guys. You're not supposed to change the wavelength. I mean to say, if you start from here, right, the wave will look something like this and end here and end here, like this. Here to here, then 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 here to here, and so on. It is actually not supposed to change the wavelength, guys. That doesn't look right. You know what I'm talking about, right, Abigail? Just, yeah. Okay, good. I think no questions are from here. Quite straightforward. This part here is a little bit harder though. I think, yeah, let me tell you a story of how to do it. And after that, you guys are going to do it yourself, okay? I'm going to teach you guys how to do this question and then you are going to do it yourself. Everyone pay attention, this is important. I've seen this come out a few times already in your IGCSEs. Okay, so how the IGCSEs will structure it is that they'll say something like, okay guys, I'm going to give you a few apparatus and I want you guys to calculate the speed of sound. Okay, you're supposed to calculate the speed of sound here. Okay, anyone has any rough idea what the speed of sound is roughly? Speed of sound in there, anyone can tell me? Anyone? Maybe Raj or Wingyan might have the answer here. Wingyan, you should know this. What's the speed of sound in air? Nine. Can't remember. Guys, listen up. This is a very important number. It's the same equivalent to your gravity. What's the gravity number again? What's the gravity number? Gravitational acceleration. What's the number for gravitational acceleration? Oh God! No one knows. What the hell? Gravitational acceleration is 9.8. No. Oh, 10 is the previous syllabus, by the way, but your syllabus is going to be 9.8. Everyone. Well, it is an important number. Yo. This number is actually very important, bro. How can no one know this? Yo. Okay, but anyways, let me get that out of the way. Everyone pay attention to this. You need to remember this number as well. Speed of sound in air is somewhere around 330 meters per second, guys. You know what this means? 330 meters per second, right? It means to say, if let's say I'm standing here and this friend is standing here and he's standing exactly 330 meters apart, if I shout at him, oi! If I shout at him, it will take exactly 1 second delay before this guy hears me. So for those who have ever, I don't know if you ever experienced this before, but this is a personal experience of mine. One day when I was very young, I decided to cycle to a very far away basketball court. And when I reached the basketball court that was like still relatively further away, I think that basketball court was probably like another 600 meters away from me. But I could see from where I was standing that there was a basketball. And the weirdest thing in my life happened. It was something like kind of broke my understanding of the world. I saw the guy, right, who was obviously dribbling his basketball. Every time the ball hits the ground, right, it will take a much longer time before I hear the sound, because you know, when you're young, if you ever bounce the basketball, as soon as the ball hits the ground, you'll hear the bang sound, then bang sound, then a bang sound, right? This one here, the ball hits the ground, come back up, then I hear the bang, then it hits the the ground again, and the ball coming back up, then I hear the bang. Then I'm like, what the hell? Something must be wrong. Then I'm like, wow, what's going on? I thought I was sick or something, you know. But then after that, I realized that I'm not sick, just dumb. I didn't understand the world enough, right? In reality, what's happening here is because the speed of sound is only 330 meters per second. It takes about 2 seconds, because I'm standing 600 meters away, right? It takes about 2 seconds for the sound to be heard. And because light travels much faster, right? So I can see the ball hitting the ground, but the sound is traveling much slower. So it takes about 2 seconds delay before I can hear the piang, the stupid basketball bouncing sound, right? So from here, I need to understand that speed travels much slower than the speed of light. That's why there was a delay. Today, if your IGCSEs ask you to determine the speed of sound, even before coming up with the experiment, right, you need to understand that speed is roughly 330 meters per second square. Why is this so important? Is because, okay, so let's say this question will give you something like this. They will say that, okay, one guy has a pistol, which is a smoke gun, you know, like those athletes, when you pull the thing, then got a big bang sound, got smoke coming out on, right? I'm pretty sure everyone here has been into a sports day before. That gun is called a smoke gun. not mistaken. But whatever, it doesn't matter what's the name called. Let's just call it a smoke gun now. And one guy will be given a stopwatch here. Okay. Then obviously they will be given a measuring tape to understand how far they are. Because if let's say you think about it, boiling down to the speed of sound, right? Speed of sound can be calculated using the simple formula, right? What's the simple formula for speed again? Speed is equals to good, excellent. It is distance over time, right? So from here, if I want to calculate the speed of sound, I need two components, right? I need the distance, and I also need the time taken for the sound to travel here, right? So let's say this is that setup right now. This is that setup right now, okay? How far do you think they should be standing apart? I give you three options, okay? He could either be standing 100 meters apart, he could be either standing 300 meters apart, or he should be standing at least 500 meters apart. How many of you guys say it's 100 meters apart? How many of you guys say it's 300 meters apart? How many of you guys say it's going to be more than 500 meters apart? Good. That is a very good answer. Why should it be standing 500 meters apart? Why at least 500 meters apart? I'll explain why, guys. Let's imagine today, right? I'm dumb, right? And I decide to stand 100 meters apart. Do you know how fast the speed will reach you? The speed, if I do some simple calculation, the speed of sound will reach you at 0.3 seconds. And we know for a fact that human beings' reaction time is somewhere around 0.7 seconds. You know what that means? It means to say that every time you hear the sound and you try to click it, right? Because your reaction time is slow, you'll measure it as a total of 1 second, which is obviously wrong, right? And every time you click it, it will be different. Every time you hear the sound, you click it, you'll hear like maybe 1 second, 2 seconds, or somewhere in between 1.5 seconds, somewhere around there. And because of that, you know for a fact that 100 meters is impossible, because if I were to try to test the speed of sound, the sound will come to me too fast. I should not use a very short distance. You guys understand what I'm talking about so far? Yeah, right. So obviously it can't be 300 meters as well, because this will be roughly 0.9 seconds, which means to say I'll have a 0.2 seconds interval between my reaction time. Is not something I want, definitely not. It should be at least 500 meters apart. Why? Because if it is around 500 meters apart, I'll have roughly 1.7 seconds to wait for the sound to reach me before I click it. Then taking into account the reaction time, maybe I'll just have like small differences between the real actual time getting there and some reaction time. Okay, so first things first, because we understand the speed of sound is around 330 meters apart, 330 meters per second, I know for a fact that I should be standing 500 meters apart. So how will the experiment go? First and foremost, this guy here is going to pull the trigger. As soon as he pulls the trigger, there will be some smoke coming out, right? Smoke can be seen by this guy because smoke is traveling at the speed of light, right? So as soon as this guy sees the smoke, he's going to start the stopwatch, and he'll wait for the sound to come, because sound is much slower, right? After 1.something seconds, the sound comes. As soon as he hears the bang sound, he's going to stop the stopwatch, right? Whatever time is measured in here, this will be the time for this. Whatever distance that you're standing, this will be the distance for this. And obviously from here, I can calculate the speed of sound. Anyone don't know what I'm talking about? Anyone not clear with this story? Anyone wants me to repeat this story again? Abigail? You understand the story? Okay, tell me how the story goes again. First and foremost, these guys should one be holding a smoke gun, and the other one should be holding a stopwatch. Good. How far should we be standing again, Raquel? Good. And as soon as the guy pulls the trigger, this guy is going to start the stopwatch. And when will he stop the stopwatch? Good. When he hears the sound, he's going to stop the stopwatch, right? And whatever distance it is, whatever time it is, I'm going to plug it into this formula and I'm going to find the speed of sound. Okay, everyone, clear? Clear as day? If it is, then guys, please proceed to do this question. I'm going to give you guys 8 minutes to write up something, okay? And please draw the diagram. It is very, very important. With your own imagination and your own understanding of this, draw the diagram, write down in words. You have exactly 8 minutes to come up with something. Huh? What? Yeah, paper. You have a different one. What? Waking up from the same. What? Okay, then write your answer somewhere at the bottom here. Oh, the question is on the screen. You may refer to it and please do it yourself, everyone. The weirdest thing. What? You can start with drawing the diagram first. Everyone, please start with drawing the diagram first. 8 minutes, guys. 11.3. Computer, it's running low. Yeah. 2 guys, one with a gun, one with a stopwatch, standing 500 meters apart, and then draw some smoke. Very good. Excellent job. Don't spend too much time on the drawing. The drawing actually has no marks. But it's definitely up to your imagination. Just to draw it as nicely as possible. Start writing down some stuff. So in the question, they'll actually give you all the things like starting pistol, stopwatch, long measuring tape, blah, those kind of things. So you want to start off with, okay, Rachel, this is how you're going to start off, okay? You're going to say something like 2 students standing 500 meters apart, measured with a measuring tape, right? One holds a piston, one holds a stopwatch. And from there, you just push it all the way already. You're supposed to describe how the experiment should be conducted. Hello. Did you need to refer to the question? I think let's do here. Yeah. What the hell are they tracking me? Done. Speed equals distance divided by time. To find the speed, you need to find out the distance and the time. One student needs to stand somewhere that is 500 meters away for the distance. 这个500 meters away， 你要想 using the this you should say using the measuring tape, measure 500 meters and then place the student 500 meters away. You have to use all the things here, by the way. Oh, Raj, I just saw your answer. Wait, let me finish this one first. One student needs to stand away from the student who is holding piston. After the piston fire, the student needs to start. After the piston is fired, as soon as the smoke is seen by this guy, you should start the stopwatch, and he will stop the stopwatch when he hears the loud bang. Then the students are able to calculate the speed using the speed equals to distance over time. Yeah, but not bad. Good. Okay, let me read Raj's answer here. All students will be holding a piston, students will be 75 holding a stopwatch. Yeah, same thing for you also, Raj. You need to mention that you may use the measuring tape here, the measuring tape here to measure 500 meters and stand where it is. Right, when the student holding the piston fires, the smoke comes out at the same instant. The student will start the stopwatch the moment it sees the smoke and will stop the stopwatch when the student hears the sound. The recorded time will be used to calculate the speed using the S equals to D over T. Time is not recorded, then divided to get accurate results. Wow, very good, Raj. Excellent answer, except for the measuring tape part only. This one here, make sure you say use the measuring tape to measure 500 meters apart. Yeah. Abigail? Hey. It looks a bit short. Two students standing 500 meters using a measuring tape. Student A holds a starting piston, holds a stopwatch. As student fires, a loud sound will take place and a puff of smoke will appear. When student B sees the smoke, he will start the stopwatch and he will stop the stopwatch. Okay, then after this one here, good. Everything here is correct already. The speed can be attained by using the distance over time formula. One last sentence. Yeah, make sure you use all the parameters. Sorry? Using the what formula? Distance over time formula. Two students standing 500 apart by using measuring tape. One is holding a piston and one is holding a stopwatch. When the student with the piston fires, smoke will come out, and when the students with the stopwatch starts, and smoke will come out, and that's when the student will start the timer. By the time the timer starts, it's already 0. Oh, you don't write this. Don't write this. You don't want to include the reaction time to calculate the speed. You didn't even talk about when to stop also. Okay, so there's a few things you're missing. You're missing when to stop and what formula to use. Okay, 2 parts you're missing. And don't include the reaction time. Yeah. I can forward this Raj answer to the group. It's a pretty damn good answer. Just need to add on the measuring tape only. Okay. 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 Yeah. Yeah. I think the rest of it, you guys do it as homework. Should be okay already. The rest of it. Okay, guys. Everyone pay attention. I want you guys to do everything from this piece of paper all the way until you see this page here on figure 6.1. Sketch the position in the wood of the 3 incomplete rarefactions here. Okay, I want you guys to finish everything from this paper. We will discuss the answers next week. Yeah. Until here, yeah. All right. Which is the end of the paper. Okay, we'll discuss the answers next week. Once we're done with this, we will proceed on with the speed chapter, guys. So please make sure you attempt your questions. It is very, very important that everyone does it. And for those who did not watch the video last week, please go and watch it. 你一定是没有看的咯，是不是？ Okay, yeah, guys. If you have any questions, you're more than welcome to stay back. If not, that will be it for today, guys. Enjoy the rest of your weekend.